Hey everyone, welcome back to ReciCon 313. Today we will look at Chapter 15, Encoding Probabilities. So we will cover mainly three topics. The first two are about why and how we can encode probabilities. And the last topic is how we can apply the encoded probabilities to solve something practical. So the first thing to talk about is why do we need to encode probabilities, okay? So as we have all learned by now, in decision analysis, we use probabilities to describe degrees of belief. So when we say something happens with a probability of 0, we simply means that the thing is definitely not going to happen. We are certain that the event is not going to happen with 100% of certainty. Okay, and when we say something happens with a probability equal to 1, we are expressing our belief that the event is going to happen for sure, for certain. Okay, and anything in between 0 and 1 just represents a degree of belief. So if I say something happens with a probability of 0.5, that expresses my belief that it is equal likely and also unlikely that the event is going to happen. Okay? We want to point it out again that these beliefs are unique to the individual who express it. Okay. Again, in this class, probabilities are subjective. In contrast, in your statistics class, probabilities are something objective that is a property of some random device. So when we throw a dice with 6 sides, if you're in a statistics class, a probability of getting a 1 from the dice simply represents an objective process from throwing the random device. However, in this class, if you say that the probability of getting a 1 from throwing the dice is equal to 1 over 6, that is your belief of how likely the event is going to happen. Okay. The thing is, when we express beliefs, we would ideally want to do it by assigning probabilities. We would not want to do that by using some English language. The purpose is to increase the clarity of thought by assigning probabilities rather than using English language. So when I say English language, I was thinking words that we use in our everyday life to express our beliefs about the likelihood of an event happening. So here I have 4 examples of those words. You might have used the word probably in your everyday life to describe an event, or likely, or unlikely, or almost certainly. These are just 4 examples that we drew from our everyday language that we use to express beliefs. Okay, I want you to pause this video now and think about the 4 words. When you say something is probably going to happen, what is the lowest probability of that event? Would you be comfortable to use the word probably? And what is the highest probability of that event that will make you comfortable using the word probably? Okay. Similarly, for likely, when you say something is likely to happen, what is the lowest probability and what is the highest probability that you mean by the word likely? Okay, you can pause the video for now and resume it whenever you have all these numbers, all these probabilities figured out. Okay. And these 8 blanks need to be filled with numbers between 0 and 1, including 0 and 1, meaning where I'm trying to ask for probabilities that you would use for these words. Okay. Okay, so here are what I mean if I say something is probably. So if something is probably happening, I mean that thing is happening with the probability between 0.5 and 0.6. Okay, anything outside of it, I would not use the word probably to describe it. So when I say something is likely, what I mean is a probability between 60% and 80%. And when I say something is unlikely to happen, I mean between 0 and 30%. If I say something is almost certainly going to happen, it has to be at least with a probability of 0.95, 95%. Okay, so these are my numbers, which almost certainly, would be different from the numbers you guys have put down. Okay, as a matter of fact, the writer of our textbook pulled all the numbers written by his students in the class and got this. Okay, so he looked at everyone's number here, and 0.7 is the highest number that people have put under here. Okay, he looked at the number his students put over here, and 0.6 is the lowest number that all his students has put under here. So as you can see, these two are contradicting with each other, right? For example, as someone like me, when I say something is likely to happen, the highest probability I'm assigning to that event is 0.8, okay? If someone hear about my statement, and if that person is this person, then he would deduce from the use of likely in my expression that the event I'm describing will happen with the probability over 0.85. But when in my perspective, that thing is happening with the probability between 60% and 80%. So as you can see, if we only use the word likely without giving the range of probabilities, or even give a precise probability for that event, it can create a lot of trouble. And words alone, only these four words without any clarification or without any precise probability assigned to it, are sufficient for representing uncertainty and for representing people's beliefs about uncertain events. Okay. And the differences in the meaning of these words across people may lead to misunderstanding, frustration, or even lack of trust. These are definitely bad outcomes from the differences in the meaning of these words. Okay. So what do we want to do? When I describe how likely I believe an event is going to happen, I would avoid using these words. Rather, I would assign a probability to precisely express my belief about the chance the event is going to happen. So the question is how? Everyone knows precision is good, but how can we achieve that precision? Is there a method or a way of thinking that can help us get closer? Okay, so the good news is there is, and we're going to show how to do that with an example. Okay, so first, let's look at a scenario. Suppose that I received $10,000 as a donation, and then I make a certificate, okay, like this. So you can imagine this as a piece of paper where I promise to pay the person who has this certificate $10,000, provided that the weight of the desk at the front of the classroom meets some requirement. Here, the requirement is if the weight of the desk is less or equal to 150 pounds. You need to pay for this certificate at some price. Okay, suppose I call a price of $1,000 and ask if you want to pay $1,000 for this certificate, and you decide whether you want to pay for the certificate or not. If you pay for the certificate is yours. And then we will weigh the desk together and you will get $10,000 if the desk measures below or equal to 150 pounds. And then you will get $0 otherwise, meaning if the weight is above 150 pounds. If you don't buy the certificate, then you don't get any payoff. Okay, so the question is, another thing I want to point out is this is based on the fact that you don't know the weight of the desk for sure, but you may have some guess or you may have some belief about how many pounds the desk is the weight of the desk. Okay. So the question I want you to consider is, when you decide whether to buy the certificate or not, what would you consider? What factors will make your decision? Okay. So of course, something we've learned before is that buying the certificate gives you some risks, right? With some probability, you will get $10,000, and with some probabilities, you will get $0. So your preference towards uncertainty, the level of your risk aversion or your risk loving would definitely be considered when you decide whether to pay the price to get this certificate. And another thing is, when I say the probability of getting $10,000, that is tied to your belief about how likely the weight of the desk is below or equal to 150 pounds. So your belief about how likely the weight of the desk satisfies this requirement is another important factor that you need to consider when making the decision of whether to buy this certificate or not. Okay, so these two pieces, both of them are essential in making a good decision in this hypothetical scenario. Okay. We've talked about the first element, the first factor in great details so far in this semester. So in this chapter, next, we're going to talk about how we can sort of get your belief about how likely the weight of the desk satisfies the requirement. So this second item here is the focus of this chapter. Okay. We're going to look at how to get your belief. So in order to do that, we're going to talk about a roulette. Okay, so how do we encode probabilities? We need to get the help from a roulette like this. So this is what we call a roulette wheel. If we spin it and with great force, and when it stops, if the needle rests in the orange zone, you will win $10,000. If the needle rests in the blue zone, you will win $0. So I believe a lot of you guys have watched televisions where there are actual physical roulettes in casinos and those places. When you spin the wheel, this wheel will spin, and then the needle will hold tight, and then the wheel will stop at a certain place. And when the roulette stops, this white needle might be in the blue region or the orange region. Okay. And here I'm showing you a special roulette where the orange color takes exactly half of the space, and the blue color takes the other 50% of this roulette, of this pie. Okay, that means you have 50% of the chance for the white needle to rest in the blue region, in the orange region, and you have 50% of the chance that the white needle will stop in the blue region. That is to say that if we do this roulette, if we rotate this roulette with this condition, you will have 50% of the chance of winning $10,000. And then you will have 50% of the chance to win nothing when the white needle rests in the blue region. Okay, so familiarize yourself with the setup. The key takeaways from this slide is that orange zone, $10,000, blue zone, $0. Okay, so what we're going to do next is we're going to use this roulette to help ourselves or to help yourself figure out what is your belief about the desk weighs under or equal to 150 pounds. Okay, so the probability of this is what we're getting at, or your belief about this, about the probability of this is what we're trying to get at. Okay, so we will put that certificate over here and we will put the roulette over here. Okay, this is the thought process that you can use to help yourself figure out what is the probability with which you believe that the weight is going to be below or equal to 150 pounds. First, think to yourself, would I rather get this certificate or would I rather get this deal? Okay, let's start with a 100% orange wheel like you're seeing here. Okay, so the deal over here with the roulette is if the needle rests in the orange space in the orange color, you get $10,000. Over here, the deal that you get if you select this certificate is that if the weight of the desk is below or equal to 150 pounds, you would get $10,000. Note, the price are the same between these two deals. Both are $10,000. Well, between these two, unless you are 100% certain that the weight of the desk satisfies this requirement, then you would choose this deal, right? If you have any suspicion that the weight might go over 150 pounds, then you should choose this orange wheel instead. So if we start with a wheel that is 100% guaranteed that you will win $10,000, you would choose this wheel. Okay, that is a super easy decision to make. Well, what if we slightly reduce the orange colored area of the wheel? What will happen? Which one of these two would you choose when that happens? Okay, let's do that. First, let's reduce the orange area to 95% of the pie. Which one of these two would you choose? Okay, well, I don't think the weight is that likely to be under or equal to 150 pounds. I would choose this roulette still. Okay, that's easy because I don't believe the. Wait, what does that mean? Okay, if you recall the 5 actions, the 5 rules of actional thought, that means you believe the weight under or equal to 150 pounds with less than 95% of the chance, right? If you choose this one. Okay, what if we further reduce the orange area of the roulette, of the wheel? What will happen then? So suppose we reduce the orange area to only 90% of the whole pie of the whole wheel. Which one of these two would you choose? Okay, if you believe this with a probability of over 90%, you would choose this one. But if you believe the probability that the desk the weight of the desk is below or equal to 150 pounds with less than 90%, then you would still choose this pie, okay? So that process goes on. So this here, what I'm describing, represent my belief. You may have a different answer, okay? However, for me, with 90% orange, I would still choose this roulette instead of this certificate. Okay, I would choose this uncertain deal instead of this uncertain deal. How about 85%? I would still choose this one in a heartbeat. How about 80%? I still think this is a better deal because I don't believe the weight of the desk is under or equal to 150 pounds with more than 80% of the chance. Okay, how about 75 pounds? Still this one within heartbeat, no brainer for me. However, it is getting closer to the point where I may consider to choose this certificate instead. So I will slow down the reduction of the pie here to help me get a more precise feeling about the choice between these two. Okay, what if the orange pie reduces to 74% of this roulette? I would still choose the bottom deal. How about 73%? Still choose this one. About 72%? Well, with some careful consideration, I think I still want to choose this deal rather than this deal. At 71%, I would still choose this deal. But at 70%, this is the point that it is hardest for me to choose between these two. Actually, as a matter of fact, I am indifferent between these two deals. Okay, I am indifferent between getting this deal where I receive 10%, $10,000 if this happens, versus this one, I will receive $10,000 if the wheel comes up with the orange color, where the orange color occupies for 70% of the whole pie. Okay, so this is the equal point. This is the break-even point between this deal and this deal. Well, what if we reduce the orange colored area a little bit more? What if we reduce it to 69%? Well, in that case, I will choose the upper deal, where I will get $10,000, where if the weight of the desk is less or equal to 150 pounds. So 69%, I switch to this one. 70%, I'm indifferent. 71%, I choose this bottom one. So that actually means that the probability that I assign to this event should be equal to the probability of winning $10,000 over here, right? I win $10,000 if this happens. I win $10,000 if orange comes up. And we know from some kind of objective measure that when the orange pie occupies 70% of the wheel, then the probability of winning $10,000 here is 70%. So when we are indifferent between these two, that means underlying in your subconsciousness, the probability that you assign to this random event is equal to 0.7. Okay, so this is how we figure out the probability. Your belief that the desk weighs below or equal to 150 pounds, and we represent that belief with the probability of 0.7. Again, here we use the notations that we've developed in this class to represent that succinctly. So you can use this process for a lot of things. Just change the upper deal to any uncertain deal that you're considering. An event happening versus not happening with the same prices. These are hypotheticals. well, I don't actually get $10,000 from a donation, but this process helps you to think straight about the probability that you would assign to this event. So this is one example of how to encode the probability for this random event. Well, so far we have encoded your subjective probability for the requirement that the desk weighs below or equal to 150 pounds. Now, suppose for some reason you need to delegate your decision to Jen, who acts as your agent. And Jen acts on your behalf and decide whether to get the certificate for you or not, okay? But the tricky thing is the teacher or the auctioneer might provide different prices and even provide different requirements to win the $10,000. So you have a series of certificates that the auctioneer might be offering to you, and for some reason you cannot be there to make the decision yourself, and you need to delegate your decision to another person. Okay. So in that case, before you leave, think about the things that you want to tell Jen in order for Jen to make the best decision for you. Okay. So the things you need to tell Jen first, of course, is your preference towards uncertainty, okay? Because Jen needs to be able to make a decision on your behalf based on how tolerant you are to the risks of winning or not winning $10,000. For that part, you need to give Jen your U-curve or your utility function. In earlier lectures, we have already learned how you can figure out your U-curve or your utility function. So that is done. Also, since the auctioneer or the teacher might change the requirement to win the $10,000, then you need also to tell Jane your belief about the weight of a desk for different requirements. Okay, so you cannot just tell her, I believe the weight is below or equal to 150 pounds with 70% of a probability. What if the teacher later changes the requirement to be, the weight being over 200 pounds or the weight being less or equal to 100 pounds? Then how far off should Jane adjust the belief below or above 70%? Okay, so you need to give her as much detail as you can about your belief about the different weights of the desk. Okay, so what we need to do is to now think about this part. Well, actually, this part we're already on the way to solve this part. We've already figured out your belief about this particular requirement, right? So the next things we need to do is to think about some other pounds. What if this is 100 pounds? What if this is 200 pounds? And then so on and so forth. And then that gives Jen more information about your belief about the distribution of the weight of the desk. Okay. So just to clarify, when we say we want you to give Jane your belief on the weight of the desk at various weights, we're not trying to ask you to give Jane a single number that represents your best guess of the weight. That is not sufficient in order for Jane to make different decisions, okay? Suppose you tell Jane, I think the desk weighs 100 pounds, okay? Then based on that single number, the information in that single number, Jane cannot have your probability assignment to different requirements. Rather, Jane needs your belief about different weights of the desk. What you need to do is to use probabilities to represent your beliefs over all the possible values of the desk's weight. For example, but you need to give serious statements of this. I believe the weight is some percentage likely to be equal or below X pounds. So before we have already composed one statement like this. You believe the weight is 70% likely to be equal to or below 150 pounds. Okay. What you want to do is to change the number of pounds, and then reevaluate the probability with which you believe the desk satisfies this requirement. Essentially, we're trying to find your cumulative probability corresponding to different number of pounds in terms of the weight of the desk. The more statements you give Jane in terms of the cumulative probability with regard to different numbers of pounds, the better she can make decisions on your behalf. So you can start with a specific requirement on the weight, an arbitrary one, and then find your beliefs about how likely the desk satisfies the requirement. We've done so for x equal to 150. Okay, so we have done this. Well, then you can put different requirements here with different weight, or even with different signs of equal or inequality. For example, you can ask yourself, what if the requirement is the weight of the desk is less or equal to 70 pounds? What would be my subjective belief for that event? Then you would start with an 100% orange pie and slowly reduce it. And what you find out is when the orange pie is 20% of the wheel, you would be indifferent between the upper deal, where the requirement is now weighed less or equal to 70 pounds, versus the lower deal, where 20% of the wheel has the orange color. Then that tells you that your subjective belief about the weight being less or equal to 17 pounds is 0.2. Okay, you can even do this with greater or equal to signs. What if now instead in the third exercise, the requirement becomes weight is greater or equal to 100 pounds? Then you would also start with a 100% orange wheel and then slowly reduce it. And when the orange area is 50% of the wheel, you are indifferent between the deal where the requirement is this versus the deal where the orange color is half of the pie. That tells you your probability to this requirement. You believe that the weight is greater or equal to 100 pounds with 50% of the chance, with a probability equal to 0.5. Okay, repeat this process for a lot of numbers and for different kinds of requirements. The fourth exercise you do is this, and the fifth one, and up to the ninth one. Okay, you can do even more if you want to provide Jen with as much information as possible to accurately represent your belief about the weight of the desk. Okay. So what now? Okay, you can give these 9 items to Jen, or you can, give words descriptions of these 9 equations to Jen. But that is not a very concise and pretty way to represent the information that you want to pass on to Jen. What we can do, like what we did with your preference probabilities, is that we can use a graph to represent the probabilities that you have assigned to all these events, okay? So what we want to do is we want to do a graph on the cumulative probabilities of the weight of the desk, okay? So here, on the horizontal axis, we have the weight of the desk in terms of pounds. It ranges from 0 to 350. Why? Because, it is certainly not that the weight of the desk is negative, right? And with 100% of probability, you believe that the weight of the desk is under 350 pounds. So we don't need to cover, 400 pounds or even 10,000 pounds, okay? And on the vertical axis is the cumulative probability. So as you have learned from your statistics class, cumulative probability represent the probability that something happens equal or below a threshold. So if we look at 100 pounds over here, and if we go up, what we need to put on the vertical axis is the probability that the weight of the desk is equal to or below 100 pounds. Okay, that is what we mean by the word cumulative. Okay, so with these two axes properly defined, we can now draw points on this coordinated graph to represent these 9 beliefs of yours. Well, the first one is that you believe the weight is below or equal to 150 pounds with 0.7 probability. Okay, so you will find 150 over here, and then draw a vertical auxiliary line upwards, okay? And the probability for that is 0.7, so you would find 0.7 on the vertical axis. Then you would draw a horizontal auxiliary line. And imagine that the previous vertical auxiliary line meets the horizontal auxiliary line at this point. Then you can draw a point over here to represent the belief numbered 1 over here, okay? So this 1 means that this point represents the first belief that you figured out with the help of the roulette. Okay, now the second one, we can do that similarly. When the weight is equal or below 70, you believe the weight is less or equal to 70 pounds with 0.2 probability. Okay, first thing, find 70. It's roughly over here, so you go up from here. And then you find 0.2 over here. So that line, the two lines intersect over here. So this point represents your second belief over here. Again, if you read down from this point, this is 70. If you go left from that point, it is 0.2. Okay. Now the third one is tricky. You believe the weight is greater or equal to 100 pounds with a probability of 0.5. Okay, look at here, the sign flipped. Okay, however, what you can put on this graph is the cumulative probability, which means you need to put the probability that the weight is less or equal to 100 pounds in the graph. How do we do that? It's easy, right? Because these two events are complementary to each other. Okay, the weight of the desk is either greater or equal to 100 pounds, or it is below or equal to 100 pounds. So the probability that the weight is less or equal to 100 pounds is just 1 minus this probability, which is equal to 0.5 in this scenario. Okay. So the first thing you would do is to figure out the weight less or equal to the number based on this, which is 1 minus the number over here. So then you find 100 over here, draw up, then you find 0.5, and then these two lines would meet over here. Okay, so that this point represents your third belief. Okay, so here it is equal to 0.5, which is 0.5 over here because it just so happens that the probability you believe with this event is equal to its flip side. Okay, and then we can do number 4, which I will not get into the details, and we can do number 5, which I can explain it a little bit more because it is similar to number 3 with a greater or equal sign. So then you need to flip the sign first. The weight is less or equal to 130 pounds with a probability equal to 1 minus 0.58, which is equal to 0.42. So then you find 0.42 over here and 130 over here. So that point is roughly, that's 7 first, roughly over here. Okay. And then number 7 here, note that it's a greater or equal sign again. So don't be fooled by that. Well, actually, it's less or equal to. I think the textbook made a typo over here. So number 7 is here. Okay, here it is a typo where it should be less or equal to. Okay. And then number 8, number 9, you got it. Okay. So now you have represented your 9 beliefs with different points on this graph. Okay. So what do we do now? When we see a series of points on a graph that seems to be following a pattern, what we want to do is to draw a smooth line to connect them. Then we can infer information about those points that are actually not on the graph, right? If we point, let's do that. If we draw a graph that goes like this, here we have some problem, but then we can go along like this. If we do that, then here, suppose you're looking at 200 pounds. It is originally not here, but for approximation, you can go to the line and then find a point over here. This point is not a point or in the original list of 9 points, but regardless, after you smooth it out with a line, you can approximately deduce that that event has a probability of, say, 0.82. Okay, so that is a good thing about using a smooth line to connect points. The more accurate you want the smooth line to represent your belief, the more points you should provide to begin with, right? Imagine you have more than 9 points on this graph, then the line may be more accurate in terms of representing your belief. But when we do that, there is a problem here, okay? So apparently, your belief number 3 and your belief number 8 contradicts each other, okay? So they are both corresponding to the weight being 100 pounds. Okay, but apparently from your belief number 3, you believe that the weight of the desk is equal to or below 100 pounds with 0.5. But from your belief number 8, it is 0.4. Okay, let's look at number 3 and number 8 over here. Well, apparently, when you do another exercise where you evaluate the probability of weight less or equal to 100 pounds, you assign a 0.4. But the flip side of this one tells you that the weight being under or equal to 100 pounds is 0.5. So how do you reconcile between these two contradicting beliefs? Well, you can do anything you want, okay? So to reconcile between these two contradictions, you can think of this as maybe I should combine the two information by crossing the line at somewhere in the middle, okay? So if I cross the line from point 2, from the second point to the fifth point, it goes through somewhere between 3 and 8. Maybe this is a more accurate one. Or maybe you made number 3 and number 8 at different points of time. Maybe before you proceed with number 8, you actually get a chance to lift the desk a little bit and get more information about the weight. So in that scenario, you would want to trust more on your belief assigned at number 8. Okay, but even if these two have the same information, if you don't gain information between either of these two, then the best practice I would say is to just get an average of these two, which is what we did over here. Okay, so as you can see, going through more exercises is beneficial because it can help yourself to be more consistent with your beliefs and then to think of things harder. Maybe the contradiction between 3 and 8 prompt you to think a little bit more carefully about your weight, that the weight is under or equal to 100 pounds, and then you would revise your beliefs to be more consistent with the other beliefs as represented by the smooth line. So here, as you can notice, we have put your name and the date and the time to the encoded probability graph, okay, to the cumulative probability graph. The reason we care about the timestamp is that it reflects the knowledge of you at the time where these beliefs are evaluated. If you get additional information, you may want to start over, then the older probability assessments may no longer reflect your belief. Okay. So the probability is what we're getting, but we didn't really use the term probability when we think about it. We used the roulette to help us thinking between choosing two binary deals. Okay. So the reason that we want the roulette to help us think about the probability is that the decision of which do you prefer, the certificate or the roulette, it is less confusing and it is an easier decision for you to make. Okay, so if we ask you bluntly that what is the probability that the weight is under 150 pounds, you may not be able to form a concrete and accurate and most reflective of your belief type of number, as opposed to think through the process with the roulette being reducing from 100% orange. Okay. So this concludes the have part. Okay, so we have by now learned how to encode probabilities. The way to do that, when we say encoding probability, we're trying to find cumulative probabilities of different measures of the event you're trying to look at. Okay, it could be the weight of the desk, it could be the time of raining in a day, it could be by how many points one team wins the other. Okay, but no matter what the measure is, we're trying to find the full cumulative probability of different values for that uncertain event. Okay, so next we're going to step into our third topic in this chapter, the use of the encoded probability. So you now encoded the probabilities of the weight of the desk. And again, you need to tell Jane, your agent, what is your risk preference. and it just so happens that you're risk neutral. Okay, so this is just an easy hypothesis that I make about you, but you may not be risk neutral. In that scenario, what you want to do is to give Jane your U-curve or your utility function. Okay, these two pieces are needed for Jane to do what? Okay, the question is now what? Now Jane can use these two pieces of information to make decisions on your behalf. Remember, the very beginning of all this exercise is that Jane can decide whether to buy different certificates for you that have different prices and then different weight requirements. Okay, so this is actually half the certificate can be represented by a binary deal. You win the certificate if the weight of the desk satisfies the requirement. You win $0 if the weight of the desk doesn't satisfy the requirement. So this binary deal represents the deal that results from buying the certificate. Okay. So now if the teacher, if the professor or the auctioneer poses a requirement such that the weight is less or equal to 200 pounds. Now the question is, what is your willingness to pay for this deal? Okay. After figuring out your willingness to pay, if the price that is being asked is below it, then Jane would buy the certificate for you. If the price is above the willingness to pay, then Jane would not buy the certificate for you. Okay, so now the requirement is the weight being less or equal to 200 pounds. Then the first thing we need to figure out is what is the probability that the requirement is satisfied? What is the probability that the weight of the desk is less or equal to 200 pounds? For that information, Jane will look at the encoded probability that you gave her. Okay, so weight being less or equal to 200 pounds, then 200 is over here. And then we would go up to the curve. Okay, and then we would go left to the vertical axis. This number would be the probability that you believe that the weight of the desk is less or equal to 200 pounds. Okay, so the probability of winning the $10,000, that is the probability that the weight is less or equal to 200 pounds by you, Mary, is 0.82. Okay, so in that case, we can simply put 0.82 as the probability of this possibility of the binary deal. Consequently, the probability that the desk of the weight of the desk is under, it does not satisfy the requirement is 0.18. Okay, then the value of the certificate for you, since you are risk neutral, is 0.82 times $10,000 plus 0.18 times $0, which is $8,200. Again, this is the expected value of this binary deal. Okay, that is your willingness to pay because you are risk neutral. If you are risk averse, then the willingness to pay for this certificate, given this belief, will be below $8,200. If you are risk loving, then the willingness to pay for this certificate, given these two probabilities, would be above this number. The fact that we don't need to go through the yield curve or utility function is because you have already told Jane that you are risk neutral. Okay. Next, this is one of the certificates that Jane can make decisions for you on. And what if the teacher now requires the weight to be between 150 pounds and then 200 pounds, below 200 pounds? What is your willingness to pay? Okay. Still, the first step is to find the probability that the weight of the desk satisfies this requirement. Okay, it is tricky because you're now looking at a range for the weight with a lower bound and with a higher bound. Okay. Still, we can use your encoded probability graph to figure out this probability. Okay, because the event can be broken down to the probability that the weight is under 200 pounds minus the probability that the weight is under 100 pounds. That gives us the range between here and here. Okay, so what we need to do is to find this probability first and then this probability second. The difference between these two probabilities is exactly the probability that the weight is above 150 pounds but below 200 pounds. Okay, so let's find this probability first. That is 0.82. We have figured this out. And the second one is 0.7. So the probability that the weight of the desk is between 150 pounds and 200 pounds is simply the difference between these two, which is 0.12. Then we can put 0.12 over here and 0.88 over here. Again, we get this number because it is the complementary event of this one. It's 1 minus 1.12. And the value of the certificate is the expected value of the certificate since you are risk neutral. As you can see, if the requirement is that the weight is greater or equal to 200, you can still do that because that's just 1 minus the probability that the weight is less or equal to 200. So no matter how the teacher changed the requirement with this encoded probability and with the information that you are risk neutral, Jane can always figure out your willingness to pay for different requirements. And then the willingness to pay again represents the maximum price you are willing to pay for it. If the price is below your willingness to pay, Jane will pay the asked price for the certificate. If it's above, then she will not pay for it. Okay. Okay, so this is the third topic. So we're technically done for this chapter, but I want to introduce another way of encoding probability that is slightly easier and may not be as complicated as the process that we looked before. But it may involve a little bit more of thinking compared to the roulette method that we looked at before. Now, as the last topic of this chapter, I want to talk about another way to encode the probabilities. So again, we're using the weight of the desk as an example. Okay, still recall that before we started with a requirement that gives a certain range on the weight of the desk, say less or equal to 150 pounds. And then we ask the question, what is the probability that the weight is less or equal to X pounds? Now, instead of doing the things this way, we can start with the probabilities and then figure out what is the pound that corresponds to the cumulative probability. That is equivalent to say that we're trying to think about the fractiles of the weight of the desk. So again, you might have learned this concept from your statistics class, but a fractile of a probability distribution is essentially the values of the measures at certain percentiles of the cumulative probability distribution. Okay, the commonly used fractiles are the 1% fractile, 25%, 50%, 75%, 99%. The 50% fractile is also called the median. Okay, so if we say the 25% fractile of the desk's weight is 70 pounds, this translates into the probability that the desk weight is less or equal to 70 pounds is 25%. Again, the fractile, the percentage before the fractile, corresponds to the cumulative probability. That is, the weight being less or equal to 70 pounds rather than greater or equal to. Okay. And also you can represent this with the notation that we learned in this class. The weight less or equal to 70 pounds, the subjective probability of that is equal to 0.25, that is 25%. And you can easily read the percentiles from the probability distribution. If we look at this distribution of temperatures, if you want to find the 25 percentile, then you would read 25 first, and then go straight down to read the temperature, which is -4 over here. Also, similarly, you can read the 50% fractile by looking at 50.5 over here, and then go down. That corresponds to 12 degrees. Okay. And we can find these 5 percentiles for this distribution of the temperature, and then we can get a table like this. So the 1% fractile correspond to a -26 degrees, and the 25% fractile correspond to -4, 0.5 correspond to 11, 75.2 27, and 99 correspond to 54. Okay, so for any distribution like this, you can read the fractiles of this distribution, these 5 fractiles. We're interested in these 5 fractiles because we're going to define the values of this measure based on them. Okay, so the first thing we want to define, the first concept we want to introduce is called the mid-range value. It is the values of the measure that are between the 25 percentile and the 75% fractile. Okay, so here for the distribution that we just saw before, the mid-range value corresponds to the values between -4 and 27. Again, the mid-range value refers to the values of the measure rather than the fractile. The probabilities correspond to the fractile. Okay, so -4 up to 27, any value between these two numbers are called the mid-range values. Okay. So the mid-range value, the two thresholds, have some properties. As you can see, it is equally likely for the measure to be inside this range and outside. So the probability that the measure falls between -4 and 27 is 50%. And the probability that the measure is outside of this range is this 25%. Plus this 25% is also 50%. It is also equally likely for the measure to fall above the mid-range value and below the mid-range value. That is to say, 25%, this range and this range are equally likely to be below 4 and above 27. Okay. And then the median value is very straightforward and might be familiar to you. So that is the value that corresponds to the 50% fractile. And the property about median value is that the measure is equally to be above it or below this value. Okay. And then we want to define what we call surprises. Okay. Surprises are the values that fall below the 1% fractile here. This is the 1% fractile. If a value falls below it, that is below -26, then it is called a surprise. And also, if it is above the 99% fractile, 54, then it's also called a surprise. For example, a 60-degree would be called a surprise. And the overall probability that the measure falls in the surprise region is 0.02 here. The probability that the measure is below -26 is 1%. The probability that it falls above 54% is 1 minus 0.99, which is also 1%. And the addition of these two are 2%. Okay, so now we know what are the definitions of, mid-ranges, median, and surprises. We can use these concepts to help us with the elicitation of probability, or it can help us to encode probabilities. We can start with surprises, and you can think about for what values of the measure do we believe that there's only 1% chance that it will fall below or it will be exceeding. Okay, those two thresholds would correspond to the two surprises. Okay, to the two thresholds of the surprises. And then you can start thinking about mid-range. And you can think about what values of the measure do we believe it is 25% likely to be below and above. And what you want to check those two properties too. Okay, if those two properties are satisfied, then you can move on. If not, then you may still rethink those measures, those mid-range values you think of. Then you can think about the median. What value of the measure do we believe it is equally likely to be above and below? Okay. When you go through this process, there are some common biases. So if you define the mid-range too narrow, then you are exhibiting overconfidence. So let's see. See, we want the mid-range values to be wide enough so that 50% of the chance that the measure can fall between it. If you are too confident with your guess, you may say the mid-range value is between 0 and 20, which does not capture the full 50% chance. That is called overconfidence. Okay. And then another common issue is to say, I have no idea about the probability. Well, usually people can actually come up with their beliefs after some reflection. If you think more about the little pieces that can give you additional information about the measure, then you can probably think out or come up with a certain kind of belief. Okay. For example, if you are thinking about what are the fractiles of a probability distribution for the number of pounds of commercial dog food production in the US, as reported in the alumnic. You might have no idea, so we're talking about the number of pounds of commercial dog food. for the entire nation. It is a daunting task to come up with medians or mid-range values or surprises. However, you can break it down to how many US population and what is the proportion of thrown away of dog food, how much does a dog eat, and how many dogs each home owns, and all those things. And probably you can come up with at least a rough guess rather than saying that I have no idea. Okay. Another word I want to say about this second way of encoding probability, that is eliciting the fractiles, is that, as you can see, it is a harder process than before when we use the help from the roulette. Okay, so but probably this way works better for you, but both ways are fine. Okay. So this is the end of chapter 15. I'll see you in the next class.